thanks to the organisers. Yeah, yes, if you want. Mine. Okay, thanks to the organisers. This is parts of this talk will overlap with things I said at the Blackboard talk about 3 weeks ago, but not completely. So I'm going to talk about phase separation kinetics in active particles. The active particles I have in mind include bacteria, which swim and then change direction in a process called run and tumble, which I'll briefly outline. Also something called active Brownian colloids, which are basically synthetic analogues of that, except that the angular motion is continuous and in small steps rather than occasional and through large angles. So the idea here is that you can get a phase separation in these systems without any attractive interparticle forces at all if the speed of the self-propulsion that these objects display is dependent on their density. So I'll explain roughly where that comes from. It's slightly surprising from some angles and not from others. What we found several years ago, and have for the run and tumble case, and have repeated recently for the active Brownian ones, is that you can get an effective bulk free energy for this phase separation through an explicit and quite precise mapping. And so, in other words, there is these systems are microscopically irreversible. They don't have detailed balance. They don't have time reversal symmetry. Nonetheless, at what turns out to be 0th order in a gradient expansion, you can map them onto a system which does have all those things. The interesting thing is that then the gradient terms break the time reversal symmetry. So I'm interested in this talk in cases where you have a theory which looks like it's an equilibrium theory for phase separation, but actually it's the gradient terms which mean it's a non-equilibrium theory for phase separation. So I'll say a bit about what those non-time reversal gradient terms look like and what they do to the coarsening kinetics and the phase diagram. And I'll say a bit at the end about Landau-Ginzburg-like models for this. No, that's not where I want to be. Sorry, I'm going to have to go back to the beginning somehow. Yeah, this comes from starting at the end. Come on. Excuse my obvious lack of professionalism here. I have this habit of making the last slide and the first slide the same, which is I've just realised that's actually a very bad idea. When you leave the talk parked on the last slide, and you think, oh dear, yes, anyway, right. Yes, well, I could do that. Yeah, that would be interesting. Okay, so detailed balance, time reversal symmetry. So just to remind you, it matters whether the microscopic equations of motion of a system have time reversal symmetry. If they do, you have something called detailed balance, which means that in the steady state, the microscopic fluxes between different configurations of the system, here marked A, B, and C, balance pairwise rather than just globally. Without detailed balance, in a steady state, there has to be a balance of fluxes, but you can have things going round and round in circles in some sense. So with detailed balance, you have a Boltzmann distribution as the only steady state, and you can do equilibrium thermodynamics, you evaluate partition function, you minimize the free energy, etc. Without, it's much more tricky. In some cases, you can map onto systems which do have detailed balance, and that will apply, as I said, at 0th order in gradients in the models I'll be talking about. But this distinction will keep coming back in the talk as to when there appears to be an equivalent system with detailed balance, when there isn't, when so on. Okay, so the two types of dynamics I'm interested in, run and tumble on the left, active Brownian particles on the right. On the left, you swim with a fixed speed in a certain direction, in a straight line, and then with a certain Poissonian process, you have a tumble. The tumbles for this talk will be treated as instantaneous, and they just reallocate your orientation of your swimming vector. And the right-hand side is the active Brownian case, which is basically a continuous version of that, where the swimming vector is continuously rotating through Brownian motion of the particle. So you have a tumble rate in one case, a diffusivity, rotational diffusivity in the other. It's clear that these processes are similar. It's not automatically clear the conditions under which they're actually equivalent, and that's something we've worked on considerably lately. There's this paper at the bottom here. In fact, we have solved the general case where you have both processes happening, so you have the punctuated change of direction and rotational diffusion. In the run and tumble case, if you just have both of these obviously random walks at large distances. V squared over alpha times dimension in the run and tumble. This expression here with the rotational diffusion constant. So they just have different angular relaxation times depending on which dynamics you have. In general, those angular relaxation times, which are in the denominator, are additive if you have both processes. And in addition, the macroscopic diffusivity of this large-scale random walk, if I have translational diffusion at the microscale as well, which with rotation I generally will have, that's also additive to D. But I'm going to ignore that. On the basis that if you have a persistent random walk, which you do in both of these cases, it's exploring space far more efficiently than a purely thermal one. So that translational contribution is generally negligible here. So the interesting case is when the parameters in these models, so the swim speed or the tumble rate or the rotational diffusivity, depend on where you are. And that's because if I just look at this, a random walk is a random walk. That system has detailed balance again. If the parameters depend on position, then life is more interesting. So any of these could depend on position. And what you can do is you can explicitly coarse grain that dynamics, and I have some slides on this which I can show anyone who's interested at the end, but they're not part of the talk. At large length and time scales, I get a diffusive type equation, so that if I have a density of particles, there's a current whose divergence is giving me the rate of change of the density. The current looks as written there. It does depend on the spatially varying diffusion constant, which obeys the formula I gave you before. The possibly surprising thing is there's also a drift velocity term in there, V, which I will show you in a minute. The lambda term is white noise, which you expect if you have a system if you go to a collective density variable. So that's just a diffusion equation with a drift term in it. The detailed balance violation is through this drift term here, which does not come from interparticle forces. It comes from the fact that there's a swim speed which depends on the density. And intriguingly, it's only the swimming velocity, not the rate of tumbling or the diffusion constant that give you this drift term. And its general form is that the ratio of V to D is minus the gradient of the swim speed divided by the swim speed, so the logarithmic derivative of the swim speed. So if I just have a system of these particles, each independently undergoing the run and tumble or active Brownian process in an environment where the parameters depend on where it is, then it's equivalent. This equation is explicitly equivalent at large length and time scales to ordinary Brownian particles in an external potential. So it's not really there, this external potential, but they behave as if it was there, and the potential is log V. And as I say, alpha and dr don't actually matter for that.
So the story I've always heard about run and tumble is that if the duration of your run depends on the local concentration, then you move chemotaxically.
That's chemotaxis. This is completely different from that. So I'm not talking about chemotaxis at all today. What bacteria actually do is they extend the run duration when they're running up a food gradient, right?
But isn't that just like changing your alpha?
Yes, but that doesn't actually come into this equation. Well, actually, no, it isn't changing alpha. Okay, I could give a separate talk on this.
Okay.
What you've just described is an alpha which depends on orientation. This is an alpha which depends on position but not orientation.
Okay.
And V here also, importantly, depends on position but not orientation. If they also depend on orientation, things get a lot more complicated, and it's not the theory I'm talking about now. So this is the simplest case where the swimming speed, that's the crucial thing, is isotropic, doesn't care which way you're pointing, but does care where you are. Right. So yeah, chemotaxis would be an alpha which depended on position and the swimming vector, which it doesn't here. Okay. Good question, though. Right, so because I have this effective potential in steady state, if I have non-interacting particles, but they all have the same dependence of V on where they are, then the density is inversely proportional to the speed. So that again is an extremely odd thing if you come from equilibrium statistical mechanics, because it says that the equilibrium steady state depends on kinetic parameters, not on an actual external potential. On the other hand, if you're a shopper, it's very familiar. If you walk down the high street, you get more people in front of a window where there's something interesting and they've slowed down. So without detailed balance, it's not actually surprising that the density depends on how fast things move locally. But it's pretty unfamiliar if you come at this from a kind of equilibrium stat mech perspective, which of course I originally did. Right, so the interesting thing now is I'm going to turn to the case where the swim speed is not prescribed in advance as a function of position, but does depend on position, but it does that through the density of particles. So this is so far effectively independent particles. It's a one-body problem, and now I'm interested in this case. So suppose I have a swim speed which does depend on the local density, then you could possibly see a feedback mechanism here, namely if the density has a fluctuation upwards and V slows down at high density, then that drop in V will cause the density to go up even more because of the top formula there. So if I have a swim speed which decreases at high density, because of this tendency for the density to increase at low swim speed, I can get into a positive feedback, and that is the basis of this type of phase separation. It's the phase separation caused by the dependence of the motility of the particles, their swimming speed, on their density.
Can you just say a few words about what mechanisms underlie this decrease in the
Well, I'll have to when I come to active Brownian. So there are many. There could be chemical signaling, which is something called quorum sensing, which in fact the one case where this has been properly confirmed experimentally in a beautiful science paper by Terence Hua and collaborators in San Diego, they actually put in by genetic engineering a V of rho, which you can do because bacteria excrete chemicals and they can sense them. So they did that. If you think about the synthetic colloids, then I'm going to turn to the case later where the actual physics is collisions. And then it may or may not be that that's well represented by a V of rho. So I was going to come back to that point. So that there could, in chemical terms, you can actually make this true in the sense that you can have a chemical field which is basically a proxy for the local density. In other situations, this is going to be some kind of mean field approximation to some microscopic dynamics that's more complicated. Does that address your query? Okay, right. So, the case which, so you can treat this interaction, there's this coarse graining recipe for the microscopic dynamics of these particles. It's a little bit technical, but you can do it. And what you can do is two things which are equivalent. One is to work by neglecting all gradient terms. The other is to say that the dependence of the velocity on the density is completely local. These are mathematically the same thing. If I have a completely local dependence of V on rho, and rho is fairly smooth, which is the same as saying that I can forget the gradients in that case, then this, although I now have interacting particles, the way they interact through this collective density field and the V depending on that is equivalent to a set of ordinary, passive, Brownian particles with that free energy density. So that corresponds to an ideal gas with a certain interaction, which again is not caused by interparticle forces, it's caused by the dependence of the swim speed on the density and the chemical potential written down there. So the log rho is like an ideal gas chemical potential, and I've got a log V of rho, which is telling me again that particles will go where V is small. That's the way it feeds through the chemical potential. So again, I'm not going to show you the mapping, but it gives you that result explicitly. So then you can have a spinodal condition on this free energy here. If you just look at the point where, if you plot an F there for the kind of S sigmoidal V of rho shown on the left here, the condition for having a spinodal instability is that the green triangle, which I've drawn there by connecting the origin to some point on the curve and reflecting it in the vertical axis, if the V of rho curve in purple drops inside the green triangle, you will have a phase separation. And that's the same as this d log rho, d log V, d log rho, less than -1 condition here. And so F of rho under those conditions has a bump in it, looks like this bottom right-hand picture. So again, although there's no interparticle forces, it looks just like equilibrium thermodynamics at this level. This level completely neglects gradient terms. Yes.
That's more or less my question. Is it conserved order parameter or non-conserved order parameter?
Yes, it's conserved.
Who grows the order parameter?
Sorry?
What is the order parameter?
Well, rho is the order parameter here.
But the dynamics are governed by gradient terms like ordinary.
Well, the rho obeys a diffusion equation, so with drift, but yes, it's indeed, it's a conservative lamp. Yeah. It isn't if you make them breed, but that's another question again. So yeah, that's you can do interesting things with putting reproduction.
I was just worried about the, you've got a gradient mobility grad mu, and does that, you assume that, does that be the next slide? That the mobility,
You'll see it. You'll see the equations motion. Okay, so at this level of a completely local V, this system, although microscopically it doesn't have detail balance, is equivalent to one which does. It's equivalent to that Brownian set of Brownian particles with that particular form for the excess free energy. And so, however, the gradient terms will break it again. So that's why the topic of this talk really is what happens when you have a system which looks like an equilibrium system, but it violates detail balance in the gradient terms of a free energy-like structure or in the chemical potential. Okay, let me carry on. So this is one of the first things we did 5 years ago now, just looking at run and tumble particles, just dialing in a sigmoidal V of rho, which you can just do. Rho then has some finite averaging range, but still you see that it phase separates in a fairly, traditional 1D way. The arrows here are the coexistence densities that you expect to get. So we have lots of 2 and 3D simulations of run and tumble as well now, and the basic phenomena of phase separation under those conditions is quite well established.
What scale of the features? Is it the initial seeding or something?
What
sets the wavelength of those features in the x direction?
Well, in 1D, it's like ordinary phase separating 1D. So you have initial noise.
Yeah.
It has a spinodal, so there is a spinodal wavelength. Now, it's true that depends on gradient terms. The density, when you do a simulation like that, you have to give a finite look-around radius to compute the local density. So that simulation had particles where V was a function of a local density, and as I'll describe in a minute, to compute that you need to give a radius to
And
it.
is that microscopic length scale that then sets the peak and the dispersion relation? Is it somehow?
Yeah, but it's ordered the run length is what
But
matters.
of course, right?
Sorry?
It's phase separated.
Yes,
Of
it's course. Yes,
eventually
exactly.
You'll wind up with a more single high density.
Yes, absolutely. So yeah, but the initial instability, the spinodal instability, does involve gradient terms, which I will talk about, but I just haven't.
That looking at the density scale sets the boundary between the domains.
Yeah. So yes, exactly. So hopefully this will become clearer. However, that was the run and tumble case, which we did first. So the active Brownian ones, as I mentioned, the natural system to think about here is synthetic colloids. You can make basically hard sphere colloids, and there's this technology of coating 2 halves of the sphere with different metals or with a metal and nothing, and you put it in hydrogen peroxide and they swim. So an interesting case, and they do obviously have rotational diffusion, so those are a viable candidate for active Brownian particles. In computer simulations, of course, it's very easy to create particles with Brownian motion and a persistent self-propulsion, and most of what I'll compare with in this talk is computer simulations. However, the key thing then is that the way in which the particles interact, if it's a purely Brownian simulation without any coupling to a fluid flow, is by bashing into each other. So the question then is that also subject to this kind of phase separation with an effective V of rho? So this addresses Suzanne's point from earlier. So certainly, and not surprisingly, when you have these collisions, because things get in your way, on average, your swimming velocity along the direction which you're trying to move does decrease at high density. That's very clear, and you can do big simulations, which we've done, and you can measure how much it decreases. In a Brownian dynamic simulation, you have you have a pair interaction as well. Well, you have the intrinsic self-propulsion and you have a pair interaction. The pair interaction is central forces, and what that means is that in a collision, your swimming direction does not rotate. So that's a defining feature of active Brownian particles with collisions. And an important caveat, which Suzanne pointed out, is that if you have hydrodynamic interactions between your particles, that's not a viable statement. If you have particles which are swimming towards each other and they have a close encounter, in general they will rotate their swimming direction and swim off in some other direction, in general.
Won't they also do that if you just have contact friction?
Yeah, basically anything which is not a central force will do that. And if you had dimers with central forces, it also would do that. So this is, in that sense, there's something quite narrow about this. But let's focus on that because that's where the simulations started off. The other thing is that, so you might say, well, okay, well, let's suppose we can do the simulation without this rotational part, no rotation in collision. But there's still obviously something going to happen. That's that I can't go to arbitrarily high densities here. Whereas if I just have a V of rho, there's nothing to stop the system phase separating to a state of infinite density. I mean, the V of rho in itself can't give you a cap on the density. Unless, well, I mean, you could design a V of rho which did, but it seems more honest to say, well, as well as using an effective V of rho to describe the system, one should introduce something else to put a cap on the density at close packing, essentially. Okay, so the question then is that picture an effective density-dependent swim speed appropriate for collisional active Brownian particles? And the provisional answers are yes. There was this paper by Cristina Marchetti and Jon Fili about a year ago now, where they found phase separating. This is the type of thing you get typically on the left. I'll show you our own pictures, which hopefully are more convincing later. So things do phase separate. You can measure the swim speed as a function of density. It's pretty linear. I'll say more about that later. You can measure the diffusion constant as a function of density, which should be v squared over a constant, and it pretty much is. So it does seem to fit with this picture of an effective V of rho driving the phase separation. And I'll show you our own simulations in a minute on that. Another paper by Redner et al. Also addresses lots of complications at high density, like ordered phases and so on. But the basic picture of like a fluid gas phase separation mediated by the fact that things slow down at high density rather than that things have attractive interactions, because all of the particle forces here are purely repulsive, seems to be a reasonably good way of describing that system. Okay, so now I want to turn back to the theory of this and say, okay, well, we did this kind of zeroth order theory. You get a mapping onto a system with a free energy that has got bumps on it, and so you do a common tangent construction, you say it should phase separate. And in principle, that's fine. If you want to know, though, for instance, about the kinetics of that, as Suzanne was hinting with those the spinodal pictures earlier, you need to know about the gradient terms in the free energy, if there is one, or at least how the system behaves in the presence of spatial variations in density and how those evolve. So the key point then is that if you formally do a gradient expansion, it's the same as saying that I can take a V which depends on the local density, but not in an exactly local way. In other words, if I write down that V is strictly a function of a smeared out density which involves some kernel here, K, that's a better approximation than saying it depends only on the density exactly where I am, which is, after all, quite hard to define. So then, and then if you look at that in the gradient expansion, that says that the density on which the speed depends is the immediately local density plus something in del squared. And the coefficient there, gamma, depends on this kernel. It's basically the second moment of that kernel. And in physical terms, it's quite easy to at least guess what that is. It's essentially the persistence length of the path. In other words, between changes of direction or on the time scale where you significantly rotate, you're sampling the density again and again along your path, and it's the average of the density. It's the dependence on that smeared out density on that length scale of your swim speed that actually is what matters. And there are various kinetic arguments that one can put in support of this. So you have some, in the expression for the smoothing length, you have something here which is a dimensionless number of order unity, the rotational relaxation time, which is 1 over alpha or 1 over d minus 1 times the rotational diffusion constant, and v itself. In other words, this has v in the expression for gamma. That's kind of important because it means that the square gradient terms are inherently non-linear if the sampling length depends on how far you get on your rotational relaxation time, and so that itself depends on the density. Right. Okay. And then we just drop this into what I showed you before, which was the expression for the chemical potential mu.
How would you encode that into the kernel itself?
Well, I mean, the kernel I'm just saying is something. I'm saying if you have a kernel, then the gradient expansion is always this form here. But as long as the kernel is symmetric, it just says that integral is equal to the value at the middle plus something in del squared. And then the amount of del squared depends on the second moment of the kernel.
So you're saying the only important parameter
Is
that comes
gamma.
out of K is this one?
Yes, yes. At this order. I mean, I could go to higher order gradients, but I don't. Peter.
So,
Sorry. Yeah, Peter first and then.
so here you've expanded rho hat
Yeah.
and argued that it comes up with a term which is quadratic in gradients. But if I thought, let me expand the velocity, and the velocity has a direction associated with it, and if I expand it to include mobilities and things like that, I might have expected the term that's linear in the gradient of rho, like n dot grad rho, where n is the direction of velocity.
Good point. It would be interesting to see if we do that and then average appropriately, you end up with something different or not.
Right.
The fact is here that at the level of description that I've got, this is a scalar theory. Everything has a velocity, but the theory as formulated is a theory for rho.
Right.
So I may touch on that point again later, but I don't think there's anything.
Well, what I'm
wrong
saying
with
is
it.
if you got to that by coarse grading of microscopic
Yes, yes.
object which had a direction
I understand.
associated.
I do see what you're saying. Yeah, yeah. If you had polar order, in other words, if you had alignment, a tendency for patches of stuff to be swinging in the same direction, then you would certainly pick up linear gradient terms involving n dot grad. But that's
People have looked at that
higher
sort
order.
of thing.
Absolutely.
You do pick up such terms, but you also get, in certain regime parameters, phase separation.
Yes.
It's like the phase separation you're talking about here, except it now has a particular directionality because the
Yeah. So there's work by Christina and Davide Maranuzzo and Fred Farrell, which actually tries to link the two as well. But I know you
There's
refer
also
to
work
others.
by Bertin.
Yes, yeah.
Okay.
Anthony, sorry.
Is the requirement that K is a decreasing function of x minus x prime? That it's
I'm assuming it's something like a Gaussian.
It's monotonically decreasing.
I think technically it doesn't. It could have wiggles on it, but as long as it decays to zero
Yeah.
on a reasonable XL. That's right.
Fast enough.
Fast enough. Yes. Okay. So, so here is what we have. So there's a current. So the rate change density is still a current. The current has a noise term, and it's got. I can write it still as d of rho grad mu. So that's kind of standard. The way in which that non-locality enters is basically through putting a v of rho hat where there was just a log v of rho in the chemical potential, and that's the right place to put it because it's still saying that you want the density wants to be where the velocity is small, and you can confirm this is within the assumptions I made that this is the correct gradient expansion. You've got this gradient term in mu, and as I mentioned, crucially, that coefficient, which is connected with the length scale of the averaging, depends on density. Right? I set beta equals 1, kt equals 1 from now on. That expression there is the formal expression for kappa that you get from the arguments I just presented on the previous slide.
So I'm just trying to, I probably shouldn't, but connect this back to sort of Carnegie to get the stuff. So the thing that goes in front of your gradient terms here, kappa, seems to actually know about the thing that actually drives the separation of dv by d rho, whereas in equilibrium that's not.
It can do, and it's the rest of this slide. So it's perfectly possible in equilibrium to have a density-dependent square gradient term, no problem at all.
Okay.
If you work out the chemical potential from that, it has that piece, and it also has this piece here.
Okay.
This piece here is emphatically absent from our theory, because our theory is derived from kinetic principles starting from the kinetics. So those equations do not have detailed balance. They do not have an underlying free energy structure. They do not have time reversal symmetry, whatever you want to call it. There is no free energy in the world that gives you those equations of motion.
But also, I think the thing that grabbed me was that expression for kappa up in the non-equilibrium one knows about where the spin-over point is, whereas, is that true in the bottom one? Do you see what I mean?
Because of dv by d rho.
Yeah.
So you mean
so
it even has sign
actually-
changes and
So
things?
actually, the
which are-
spinodal, that becomes very small.
That's a good point, actually.
Yes, it's
Yeah, it's a good point. So there's some linkage between the gradient terms and the non-gradient terms, which it would be very surprising in itself in an equilibrium system.
But does that cause you problems with your length scales? What in the dispersion relation actually? Well, that's spinodal. The dispersion relation is marginal anyway. But,
I don't. We haven't seen any problems with that, but you're asking an interesting question.
yeah. And also, if you approach somehow a critical point, then diverges at 0 times. I'm getting a bit far-fetched now, but anyway. Well, I mean, in equilibrium, it would. Do you see what I mean? So, I think I'm
Yes.
getting a bit far-fetched now, actually.
No, I think it's an interesting point.
Yeah.
So you're looking at the dynamics of the first order dynamical phase transition.
See, no, actually, this is not quite right, Suzanne. dv by d rho, as opposed to d log v by d rho.
Oh,
d log rho. dv by d rho is always
You're right.
negative.
You're right, sorry, yeah.
So kappa doesn't change sign, and it doesn't do anything spectacular.
Okay.
It is conscious of the v of rho curve, but not in a way that links directly to the f. Yeah, okay.
No matter how many times I read your paper, I always have dv by rho to log
I'm sorry.
in my head.
Okay, right.
My head is better than yours.
Okay, so then the interesting thing is that we have this theory which doesn't have detailed balance. The only reason it doesn't is because of the gradient terms. And also, what's more, we know how to construct exactly the same theory and put detailed balance back if we want to. We just add this term here.
This model's got its analogues in surface growth.
Indeed. So this is something I learned from you last time I was here, that this is not the only place where you get non-integrable features in this sort of position in the theory. So So I need to learn more examples of that, although I did read the one you sent me. Okay. So, and you even mentioned earlier in the previous talk something about breaking the common tangent construction, and I'll say exactly how that happens here. Okay. So, right, so there it is. So there's two aspects to this. One is I want to take in two different directions in my remaining time. One is to show you that if you take this at face value and you code in v of rho that you've accurately measured from a simulation of active Brownian particles, that this theory works pretty well. And then I want to address the generic issues of having a theory in which detailed balance is violated only in the gradients, which connects to the point we were just making there. So first things first, let's just see how well this works for active actual Brownian particles. So we've done a lot of simulation of this, mainly Joachim Stenhammer, who's in Edinburgh at the moment. So here are the equations again, just as I wrote them down before. And I did mention, though, that we need one more thing, which is a bit empirical, which is to put in something to stop the density diverging in the dense phase, because that's to do with excluded volume and crowding, not to do with V of rho. So we're hoping that the main features of the phase separation are driven by V of rho, but that somehow there must be a limit to the density, otherwise for typical V's this is going to send the density off to infinity. Empirically, if you measure what V of rho looks like, and you do that by doing a big simulation, and you can do that in the single phase region before you phase separate, you can measure that as a function of density by looking at the projection of the actual velocity along the self-propulsion direction. So there's a clear definition of V of rho, and it essentially decreases linearly. So, I mean, it's amazing how linear it is. I'll show you in a minute. But that's just an observation. So you can put that observation into your theory, and then something to stop the density diverging in the dense phase. So V of rho, if you put in that linear form, and gamma naught, I need a single order parameter, order unity constant to set this sampling length. Then those things together determine both D and kappa. So there's nothing else left in those equations to work out. Everything that goes into them comes out of the simulation that you're trying to match, except for the repulsive bit.
Excuse me?
Yes.
Any special reason for the exponent 4?
No, that's just completely empirical.
It's just supposed to be big at 1.
Yeah. Yeah. I think it's been used for yeah, well, I don't know where it came from. Right, so that black curve there is just showing you that it's linear, and v squared over tau r should be, and tau r is a constant, the rotation time, that should be this kind of funny quadratic thing. That's the red curve, and the deviation is in blue. In other words, the constancy of the blue line is telling you is confirming this relation between V of rho and the diffusion constant. So that's pretty accurate, at least up to about 0.8. So given that the action here is at lower density than that, this ought to work. So let me show you. This is active Brownian particles. So as a phase separation, this has some interesting features. I mean, it's very vibrant. It looks very hot, actually. And you quite often see, bubbles of the wrong phase, which even sometimes drift out of the middle of one of these things and collect with the other. So it's a bit unclassical in the way that behaves for a phase separation. Though I do think that if you took a standard equilibrium model and you made it hot enough, it would also look quite like that. It's obviously not, you have to be still well below the critical point. But we compare that with the continuum version, so this is actually using the kind of optimized free energy function that I said before. Well, it does a reasonably good job. You don't see as much of this throbbing of formation of little pockets of the continuous phase inside the droplets, so you do see fairly big fluctuations there. So it's okay. I wouldn't say it was perfect, but it's certainly a usable continuum theory if you're interested in the macroscopics of phase separation.
Switch off the noise.
Sorry?
Suppose you switch off the noise, get rid of the fluctuation.
Yeah, well, you can of course switch off the noise, but one thing I should say is that in the continuum theory, the amplitude of the noise is not negotiable. We derived it. I mean, it comes out of the derivation of D and the density. So we only put in the right noise. It's certainly true if we just turned our noise down, we'd get something more like that.
Because the pattern formation in the structure that you're getting there, it looks like the noise is just a superposition on top of that.
Yeah, I agree. And in a sense that comes through in what matters, which is this. So this is the length scale. So this now has only one fit parameter, and the black curve is the active Brownian and the red is the continuum model. So the first and important comment is those curves actually join up with only one parameter. The exponent appears to be a little less than the standard 1/3 value, which is what you would expect with a equilibrium system. But in fact, that is, well, I'll say in a minute what we think that is. Let's see. Yeah, so that's the first comment. The red curve is 2 decades beyond the black curve, and that is how far you can get with the black curve, even with the country's fastest supercomputer, which is now in Edinburgh. So if you want to look at this at long times, the continuum theory is going to give you stuff that you couldn't otherwise reach, including, for instance, a reasonable statement that slope is not quite 1/3. On the black data, you'd be pushing it.
Model B is just conserved.
Yeah, so model B is, I'll come back to it, of course, but it's just the standard one without the that detailed balance violation. And it's, 5-4.
The fluctuations of the boundary and you think of surface tension, and the effective surface tension is a bit strange here because it's rho dependence. But does it behave like a ordinary surface tension?
Well, to get those,
It must in some sense.
to get those two simulations to look like each other, you do need that. If I replace the square gradient term in the continuum simulation by a constant, it is much less nice in how it looks like the
Because
other
when it's
pictures.
formed a well-defined interface, there will be a value
Yes.
for those gradient terms there, and if you could put that value in, it doesn't behave the same way.
I don't think it does, because the interfacial profile, if you look at it, it's not a tanh chart. It's exactly the
It's
same
something
before.
else, yeah.
It's something else,
Yeah.
and it's got a bit of a tail out into the dilute region. So so if you want to make it look, a nice match, then we found anyway that you pretty much, it certainly looks better with the parameters that come through the mapping as the choices rather than ones that you would default to. The other interesting thing is, by the way, is that the default for the square gradient terms is of course a constant. That keeps the detailed balance. So you have to be very, very careful not to default to detailed balance in a system which doesn't actually have it. Having said that, this shift in the exponent doesn't seem to be because of that. I told you how to put the detailed balance back, which is just to add that term, which creates this, it effectively recreates a free energy with a density-dependent square gradient term. And it doesn't seem to change the exponent. So whether that exponent is really different from 0.33, I'm not sure. There are mechanisms where you have a strongly density-dependent diffusivity that have been explored in that paper by Bray and Emmett, where at least in some interval you might appear to get a different exponent. To get an actually different exponent, they have a diffusivity which vanishes strictly vanishes in both phases, and then you can get any exponent you want, depending on how it vanishes. So we do have a case where the diffusivity is becoming very small in the dense phase, so it's possible this is connected with that, but I wouldn't like to speculate further. The one thing, though, is it's not just coming directly from the dB violation. Right. Oh, let me just show you a couple of 3D results. For this, you really do need a supercomputer. This is 8 million active Brownian particles. And it looks just like ordinary phase separation. And so does the continuum theory, which I'll show you now. And as I say, this runs 100 times faster, so it's worth knowing that you can get a continuum theory that seems to correctly encode the active Brownian
Do you
thing.
find the exponents the same in 2D and 3D?
In 3D, they're harder to measure, of course, because the system is smaller. Are they the same? I would say that the 3D one has an error bar, which could be a third, it could be the 0.28. I don't think we know that yet.
Theoretically, it's supposed to be independent dimension.
Yeah, it should be a third. Yes, it's basically just it's the same as the Ostwald law. It's just the R dot goes like 1 over R squared. Okay, so let me summarise that. In the case where you have active particles whose motility parameters, specifically the swim speed, whether they're run and tumble or active Brownian, where that swim speed depends on the density, then you can go through this explicit coarse graining. You can get a mapping onto a system which has got a free energy and therefore has detail balance restored at 0th order gradients. The square gradient terms break it again. If you take that, the path through to this this rather specific square gradient theory with the V of rho setting the specific f, you get very good agreement between the two sets, between the continuum and ABP, at least much better than I was expecting. Oddly, the detail balance foundations are there at square gradient, but they don't seem to affect phase separating kinetics. And if there is an exponent shift, it's possibly to do with this D of rho. One way to explore this is to do it with a constant d, which I'll come to in a second. But we found something quite intriguing, which looks like a numerical artifact, but turns out not to be. That is that if you carefully do the active Brownian, the continuum and the version with the restored detail balance, so with the same d of rho and a kappa, but with a term which gives you a free energy again. Firstly, note there's a bit of a mismatch, which I think is between the active Brownian and either of the two continuum simulations. What's plotted here is actually just the histogram of the density. So you should just get two huge peaks at the coexisting phases in this. This is just what you should see. The coexisting phases in the simulations, the continuum simulations are not quite where they should be, but then we had this rather ad hoc high density piece which may be responsible for that. If you don't get the density quite right in the dense phase, of course, the common tangent will give you the wrong coexistence as well. But interestingly, there is a definite small shift between the continuum theory without detail balance and the continuum theory with detail balance restored in the phase diagram, in the coexisting densities. So this puzzled us, but it wouldn't puzzle you.
No, it makes sense to me too.
Yeah. Well, let me just show you how it goes. So, how can gradient terms change the common tangent construction? Well, look at the common tangent construction. This construction only appears to use the bulk part of the free energy, and the word appears is obviously important. So what I had expected was no change there. We were expecting bigger change in the kinetics, but actually the kinetics are almost unchanged. And so let's turn to a simpler model just to nail this right down, and we've nailed it right down as to what's happening in this particular type of system, and it may well overlap with things which you already know, in which case I need to hear about it. So forget about the particular form of f of rho, let's just turn to a double well potential standard 5-4 theory. There it is. So I have a thing like a free energy. Well, I have a free energy. Suppose I have got a free energy. That's the chemical potential. And now I'm going to break detail balance by adding to that a non-integrable piece which is there. And that's exactly what you get if you have a constant derivative in the previous theory. So in fact, k of rho is some function of rho. If it were just linear, this is the non-integral piece you get. So I can talk about that chemical potential, this model, forget about the noise, you can put it in if you want. So there's a current minus the gradient of the chemical potential with the non-integral piece in, phi dot is minus div j, perfectly standard. That is model B, except for lambda. So active model B. So I think that's an interesting theory. Whether it exists or not, I'd like to know. Whether it's been studied before, what I mean by that. But let me just show you what we found out about it so far. Firstly, yes.
Sorry to interrupt you.
Yes, please.
Even once you get the gradient terms specified right to get, I guess, what in shear banding language would be the stress selection right, is that what
Yeah, well, that's kind of what we're talking about.
But would you really expect it to be that reproducible? Because actually one of your phases is in the jammed phase, so that's more like shear banding in a soft glass, where the low shear phase is jammed and therefore not necessarily reproducible depending on...
Yeah, I accept that in the context of the ADPs.
Yes.
I'm talking now in a completely abstract sense about this theory. Yeah.
But if you actually did the simulation and
I
it's
agree.
been jammed up, then...
I agree. So, but if I was going to say anything about simulation here, it would be simulation of these equations direct.
Right.
I'm no longer talking about ADPs. I'm talking about the generic consequences of detailed balance violation at gradient level in a theory which is trying to phase separate. Yeah. Okay. So, right. So I have the equations of motion as well. So first thing, you can simulate it. This is Adriano Tirabocci has done these simulations. And you can do it, obviously, well, this is the one case where you know you're going to see a third if you turn off that lambda term, because that is model B, and that's being simulated to death, and it is a third. If you turn on lambda, the exponent seems to drift down, but again, I wouldn't want to put much weight on this. And I know what is needed to actually nail down an exponent, and it means doing decades of simulations of adjusting the parameters to make them all. We haven't gone on to that yet. Nonetheless, apart from a possible small shift in exponent, the kinetics doesn't have any special features when I turn lambda on, so much so I'm not even going to show you the movies because I'll be wasting my time showing you two identical movies. They do look like the ones you saw before. Okay, so what's happening? Well, one thing we do know, so this is the equilibrium construction, of course, you just draw the thing across, and 4 of 5 for potential symmetric, it's just a horizontal line, the common tangent. So the normal statement is in equilibrium, the chemical potential and the pressures have to be the same. Now, so that's the usual thing. So it's worth thinking a little bit about what changes here. What changes here is the chemical potential still has to be the same. And that's because the gradient term is only non-zero at the interface. So in the bulk phases, the expression for the chemical potential is the same as it was. And what's more, J equals minus grad mu. So a steady state in which I don't have a constant flux of stuff through the system from one side to the other has to have mu uniform. But it doesn't have to be zero. So you still have this, the common slope, but you don't have to have equal pressures. And it's interesting to think, okay, so that's the uncommon tangent construction. It's interesting to think about these pressures. So firstly, you can, this is quite an interesting model because you can calculate that completely. Well, no, the green curve is numerical, but it comes from just solving the equations of motion at an interface, which is tanh with corrections. You can do it perturbatively for small lambda, and you can find that coefficient there. So there's always is an interfacial profile that exists connecting two densities, which isn't in itself obvious, actually. You could imagine that at high enough activity you would destroy a profile that connects two bulk phases, but you don't. And what happens is that the offset in the chemical potential, or equivalently the mismatch or the pressure change, saturates. So if you draw the free energy curve here, there's a maximum pressure difference you could ever get between these two phases, because there's a maximum slope I could draw on this branch of the curve, which actually passes through this spinodal point here. So that's the maximum pressure difference, and that's what you get in the limit of large lambda. Okay. So the next question is, is that really a pressure? Now, this is a very, very awkward point, because this whole free energy was developed by analogy, as through a mapping. But one thing we can ask is, can I balance that pressure with a Laplace pressure? And if I can, then at least it has some reason to be called a pressure. And the short answer is I can. So the explicit calculation tells you what is this pressure jump across a flat interface at small lambda, perturbatively 8/15 lambda. The theory, as I wrote down with the unit coefficient of the standard square gradient term, also has an interfacial tension. So I can write that down as for lambda equals 0. And I can calculate the Laplace pressure as the pressure difference across the curved interface of a droplet. And explicitly, yes, if you balance those two, so here, you can have a stationary solution which directly connects the -1 minimum of the free energy to the +1 at exactly the radius at which those two terms cancel each other. So there is, at least in a thermodynamic sense, a reason to call this a pressure. So what we have then is, in the context of the active system, what you have is the square gradient term. What it looks like is that the activity or the non-detail balancedness of that term is effectively giving you a pressure jump across a flat interface, which can then be compensated by curving the interface.
Does that mean that when the thing courses, it's going to stop at this radius?
Excellent question, and I'm so sorry. The answer is no. So here's this. You're really ahead of us here, Tom. Okay, so there are stable droplet phases in active colloids. It's quite a mystery, certainly in fact, well, the usual claim is that you add a bit of attraction and then you can get clusters which don't grow any further, paradoxically. You can get phase separation in repulsive particles. If you want them to not phase separate completely but stay a finite size, you add an attraction, which is extremely unintuitive, but that seems to work in both the bacteria and the synthetic ones. But yes, could you get a stable phase where the droplets reach that size and stop growing? And sadly not. And the key to that is a diagram which is kind of standard in the Ostwald-Reifning literature, and that's to plot the rate of change of size of a droplet against its current size. And this picture is exactly what you draw for an ordinary droplet in contact with its vapor. And what's happened here is that everything's shifted. So the equilibrium, normally with a spherical droplet, it would have a static solution in contact with a vapor pressure which was not zero, or the phi outside wouldn't be quite zero. So you'd have to balance the Laplace pressure with a slight shift in the chemical potential outside. Here you don't do that. You can do it at zero chemical potential, but it's still an unstable fixed point. It's still, every droplet will grow faster as it grows and shrink faster as it shrinks. So sadly, I cannot explain a microphase separate state or a stable droplet phase like this, which I must admit is what I was hoping to be able to do, but sadly ain't there. At least we've not found it yet. Okay, so we're very near the end now.
Will it be too far-fetched from an active model B to get to an active model H, which might actually have a resident?
You're both ahead of me, but at least I have got the slides there.
What's model H?
It's got coupling to momentum. So it's model B coupled to a fluid flow, and here it is.
Oh.
So, okay. So this is an interesting point, and I have another slide which I'm very happy to show you, Suzanne, but I'm not going to broadcast to the world yet. But this is what you would do. This is what model H would look like. If lambda was 0, what I've drawn there would be model H. So you have a chemical potential, you've got the advective diffusion equation for phi, so you've got the fluid wafting you along as well as diffusion. And then in the Navier-Stokes equation, you have to put in a stress term, which cares about the disposition of the Euler parameter. And in standard model H, that stress is coming from the Laplace pressure. Basically, it's saying I've got interfaces, they have curvature, that creates pressure gradients, that creates fluid flow. So that is standard. Lambda here, we have to worry about. What I'm going to say, though, is that the thermodynamic proper model H with lambda equals 0, for which we know the stress, it's the pressure plus something involving the gradient terms, is no guide to what needs to be done for active model H. And that's because the reason you know this form of the stress tensor in the conventional model H is because you know there's a free energy. And the reason that the free energy connects to the stress is because ultimately the reason the free energy is what it is because of the interparticle forces. So we were playing around with this for a long time before I realized that we were barking up completely the wrong tree. If the non-lambda terms here come not from interparticle forces, but from the fact that things slow down their swimming, there is no link of anything like this nature between the effective free energy and the stress, which is partly why my issue about whether this funny pressure was really a pressure is still pertinent. That funny pressure is really a pressure in the sense that I can balance it against a Laplace pressure, but the Laplace pressure is itself not really a Laplace pressure either, because all of this is coming from a V of rho and not from pair interactions. So the mechanical stress only links to the free energy because of the statistical mechanical statement that the free energy is what it is because there are forces between the particles. And the more you think about that, the more you realize there is no link between the functional form of this kind of free energy, which comes through this mapping from V of rho, and the stress. Luckily, I think we do know what the stress should be, but I'm not going to video it across the world at the present time. Okay, so I think that's the end, and thank you for your attention.
Yeah, so the non-integrability is very similar to the shear banding.
It is, isn't it? And
Because in our case, the non-integrability comes about from not the gradient terms, but the co-rotational derivative. But
yeah.
Even so, the whole dynamics is non-integrable, which means that it depends on the shape of the interface.
Yes.
And in that case, the gradient terms will always make a difference. So in this case, it's also non-integrable because the gradient terms, and either way you slice it.
Yes, I think maybe the thing which is strange is that the implicit belief that if you have the bulk free energy, you have the phase diagram.
Yeah.
Now that's true if the gradient terms don't violate detailed balance.
Exactly.
If they do, then the link which connected those two things is broken, but it's broken through terms that you haven't bothered even to write down yet. So yeah, so I agree that mathematically it's quite similar to what you have in shear banding, and probably, as I hope maybe you'll tell me later, other examples as well, I expect. Yeah, so anyway, that's how it shows through here. And I think the idea that I mean, I don't know whether this idea of getting a static pressure jump across a flat interface is useful. The interesting case here is that the chemical potential really is equal.
Yeah.
So it's only the pressure that's different in the two phases, and I don't know how generic that is either. Because in general, if you had a different equation of motion, you wouldn't have to have equal chemical potential. It's only because the current depends on the chemical potential and the gradient terms vanish in the bulks that the two chemical potentials have to be the same anyway, but not the pressure. Yeah.
If you have this droplet stable or
stationary unstable solution.
So how does it decay far away from it? Does it decay like asphalt? And I mean, the tail is important for the cosmic kinetics.
Yeah, that's a very good question. That's a very good question, and I don't know the answer, so it's something we should look at. Yeah, good question. In the simulations, even in droplet phases, coarsening kinetics seems to be, quotes, normal. So my guess would be that it's the same sort of concentration field as in the standard equilibrium case, but just with these shifted chemical potentials. That would be my guess. Suzanne?
So in model B, if you just make a list of all the parameters in the model and look at their dimensions, then to get this coarsening exponent, all you do is combine those, and there's only one way to combine them to get a length as a function of time, and that's the time to the third way, which is your 0.33. So if you write down all the parameters in your model and identify their dimensions, is there some way of, I mean, 0.28 is a bit of a weird thing to end
I know.
but it's just the whole dynamical scaling stuff and whatever.
Well, yeah, so I mean, it's, what you say is not strictly true, because you have to first convert the gradient terms into a interfacial tension, I think, before you can really make that. So, yeah, in that sense, so that's something that you've described in previous talk. So then it's not clear what lambda will do there, because it's part of the interfacial physics, which could cock everything up.
For the active model H, yeah, I mean the non-model H, there's this other formulation where you write the stress tensor, the gradient of the stress tensor as, I think it's rho grad mu.
It's rho grad mu, yeah. So div sigma is rho grad mu if you take that standard thermodynamic expression for, yes, indeed.
And so this grad mu, would that be a good first try with
Well,
mu?
Well, that's something you could do, would be to stick our mu into the rho grad mu there. And we played about with that a bit. And then I reached this conclusion that that's a false path, that you have to directly connect the mechanics of the swimmers to the stress rather than try to do it through the thermodynamics. Because I just think that link is broken. I mean, you could write it down. I just don't think it would describe the actual physics of the self-propelled things. By the way, of course, there's an interesting case, which is when you see the equilibrium part, the bit of the free energy which has detailed balance, even though it came from a theory which doesn't. Of course, that free energy, the fact that you've got a phase separation, could come from any number of combined sources. So you could have a system in which that free energy was mainly conventional thermodynamic phase separation. You could have attractive particles, have a phase separation because of that, and then think about what happens when you make them swim a little bit and you just tweak the gradient term so it suddenly becomes non-integrable. And I think that's a very interesting case as well. And then I'd be quite comfortable with what you're suggesting. But that's not the case where everything comes from V of rho. Yeah.
I have a very basic question, because you had this rho hat, which was a kernel integral over rho.
Yeah.
But how do you define rho without a hat?
It's technically, it's a very good question because
there must be some coarse graining in rho.
Yes, indeed. So the uncoarse grained rho is a bunch of delta functions.
Exactly.
So that kernel is then counting the number of particles in your neighbourhood within a certain range. So if I want to do a gradient expansion on that, then I have to make the kernel much wider than the spacing between the delta functions, and then it starts to work. So to be able to use that, what you'd like to do is say that because the kernel is basically set by the run length of this persistent random walk, you'd like there to be many particles in a volume swept out by the run length, and then you can start to use gradient expansion. If the density is too low, it doesn't make any sense at all.
Take one final question.
Yeah, I want to make a parallel between this invariance of the scaling under the presence of this non-equilibrium part. So model A, I think that's the non-conserved.
Non-conserved version, yeah.
So model A, model B, you can perturb model A with a non-variational term, a grad phi type, and that naturally does not perturb the scaling. But if you perturb model B, there's two options. There's grad phi inside the Laplacian, which is essentially what you've got, or grad phi in the outside. If it's on the outside, then it does perturb, and it goes from T1 third to T1 half. But if it's on the inside, I suspect it's like model A.
So I need to check that, but if I have a density-dependent mobility in model B, then as long as that goes between the two gradients, it's still a fully free energy-based model. And as long as that density dependence is in the mobility is bounded and doesn't do these extreme things which Bray and Emmett looked at. So in that sense, that's still got detailed balance.
Yeah.
If I put a term in outside the outer gradient, then that suddenly is introducing something like a drift velocity, and it's more like this. So yeah. So I mean, if there's a literature on that, it would help me a lot if you can tell me where to find the previous references there.
Okay, so we should probably stop and go get some food.
Yeah.
Thanks a lot.